This lesson will focus on the Class B multi-engine performance requirements for the en route and descent stage of flight. Essentially, the en route part of the flight is considered to be from 1,500 feet above the airfield from which the aeroplane has taken off to 1,000 feet above the destination airfield. As with all the other requirements we have come across, the en route and descent requirements are written in JAR Ops 1 and abbreviated into CAP 698. However, the abbreviated version in CAP 698 is very clear and almost word for word like the original requirements published in JAR Ops 1. Therefore, we shall work through the en route and descent requirements using CAP 698. At the top of page 17 of section 3, you can see the en route requirements. The first sentence simply reminds you what the en route stage of flight is. The requirement for the en route stage of flight is that in the event of engine failure, with the remaining engines set at the maximum continuous setting, the aeroplane must be able to continue flight at or above the relevant minimum safe altitude to an aerodrome at which the landing requirements can be attained. This requirement is almost identical to the single-engine aeroplane. The only difference being that whereas the single-engine aeroplane has to be capable of landing in a suitable field after engine failure, the multi-engine aeroplane must be capable of a higher performance and therefore continue flight and land at a suitable airfield. Therefore, in the event of engine failure, the multi-engine aeroplane should have a level of performance such that it can, even with an engine failure, get to an airfield to land. However, as with other requirements we have covered, the en route requirements do have some compliance rules. In fact, these compliance rules are very similar to the ones we mentioned in the single-engine en route lesson. In order for the pilot to be able to abide by the regulation, the descent range with one engine inoperative must be known as well as the one engine inoperative cruise range. Once these have been calculated, a flight track must be plotted that will ensure an airfield is always within the total one engine inoperative descent distance. Herein lie the compliance rules, because the compliance rules relate to how that descent range is calculated. The first compliance rule states that the aeroplane may not be assumed to be flying above the altitude at which the rate of climb is 300 feet per minute with all engines operating. You may recall from the single-engine en route lesson that this doesn't mean the aeroplane cannot operate higher than this altitude. It most certainly can. What the compliance rule means is the aeroplane must not use the extra altitude above the 300 feet per minute altitude to gain extra range to help comply with landing at an airfield after engine failure. The second compliance rule states that the one engine inoperative net gradient of climb is the gross gradient of climb decreased by 0.5%, or the net gradient of descent is the gross gradient of descent increased by 0.5%. What the compliance rule is saying is that when calculating the descent range to work out if the aeroplane can make it to an airfield, the gross gradient of descent must be increased by 0.5%. This adjusted gradient is the net gradient, and it is simply adding a safety margin into the aeroplane's descent range. In this case, an airfield must be within the net descent range and not the gross descent range. Calculating the descent range of a twin-engine aeroplane after engine failure is not as easy as it was for the single-engine aeroplane. For the single-engine aeroplane, to calculate the descent range, it was simply the height of the aeroplane divided by the gradient and multiplied by 100. However, the gradient of descent of a twin-engine aeroplane following engine failure is constantly changing. Let us explain why. Shown here is a twin-engine aeroplane, a Piper Seneca, in straight and level flight with the forward force of thrust balancing the rearward force of drag. When the engine fails, notice that there is more rearward force than forward force, and, as a result of the excess drag, the aeroplane will slow down if level flight is maintained. To maintain the speed, which should be kept at VMD, the thrust force generated by the remaining live engine must be augmented so that the forces can once again be balanced. The only way to do this is to lower the nose so that weight can act forward and provide enough weight apparent thrust to balance the excess drag. If the nose is lowered by a sufficient amount, then the forces will once again balance and VMD can be maintained. The only side effect is that the aeroplane is descending. However, as the aeroplane descends in the atmosphere, the air density increases. This means that the thrust being produced by the remaining engine increases, which reduces the excess drag. Notice now that there is no need for so much weight apparent thrust, since the excess drag has reduced. To reduce the amount of weight apparent thrust, the nose is raised a little. This process can continue until the remaining engine generates sufficient thrust to balance the drag without any need for weight apparent thrust. At the altitude where this balance occurs, the aeroplane is able to level off. In summary then, after engine failure in the cruise, the aeroplane is forced to descend. But as it descends, the aeroplane can slowly reduce the descent angle until the aeroplane can once more fly level. This procedure is known as the drift-down procedure, and it produces a drift-down flight profile similar to the one shown on screen. It was stated that calculating the descent range for a twin-engine aeroplane after engine failure was complicated, and the reason, which is now hopefully apparent, is that the descent gradient or descent angle is constantly changing. In the absence of a drift-down graph, the only feasible way of calculating the descent range is to break down the profile into manageable segments and carry out several calculations, as shown on screen. Each of these calculations will need the net descent gradient at that altitude and the vertical interval of that segment. This will give the horizontal distance covered for that segment. To find the descent range, simply add all the horizontal distances in all the segments. After the descent range has been calculated and the aeroplane is able to fly straight and level, the last remaining information that is needed is to find out the one engine inoperative cruise range. Once this is known, it can be added to the descent range of the drift-down profile to give the total range of the aeroplane following engine failure. Therefore, at any point along the flight, there must be an airfield at which a landing can be made within the total range from engine failure. To ensure this, a circle whose radius is the total single-engine range is drawn around each airfield between the departure and destination points. To comply with the regulations, the aeroplane track must fall inside these circles. In doing so, the aeroplane will comply with JAROPS 1, which states that in the event of engine failure, the aeroplane is capable of continuing flight at or above the relevant minimum altitudes for safe flight stated in the operations manual to a point 1,000 feet above an aerodrome at which the performance requirements can be met. If during some of this lesson you were unsure of the calculations and formulae needed to work out the horizontal descent distance using the gradient and height of the aeroplane, then please go through those parts of the climb and descent lessons in the General Performance Principles section that detail the use of those formulae. Practice using the formulae and go through the questions at the end of the lesson. These calculations form an integral part of the exam and your life as a pilot if you're flying Class B aeroplanes. You should have learnt two main points from this lesson. Firstly, you have learnt what the en route and descent performance requirements are that govern multi-engine Class B aeroplanes and where to find them. And secondly, that the pilot must comply with these regulations when operating a multi-engine Class B aeroplane in the commercial air transport category.